SwayamPrabha. Digital India. Educated India.
Very good afternoon. I welcome you all to the session of Thermal Engineering Basic and Applied, and today we shall discuss about the compressor efficiency, and then we shall start our discussion today on another aspect of the gas turbine units, that is the multi-stage compression with intercooling. So, in the last class we have establish the mathematical expression of work done needed to be supplied to run the compressor, following several processes, and those processes are reversible adiabatic compression, reversible isothermal compression, and a more generic process, that is reversible polytropic compression. So, if we write here that compression work following a reversible polytropic process, then this expression should be this n by n minus 1 then P 1 V 1 P 2 by P 1 to the power n minus 1 upon n minus 1. So, this is the expression of the work done needed to be supplied to the compressor while the working fluid will be compressed following a reversible polytropic process. This negative sign, as I said you, that this is basically an indication of work input to the system, following the notation that we could write in the last class, that work added to the system is negative, work extracted from the system is positive. Now, today we shall discuss graphically that if we try to map the compression processes in PV plane from a graphical representation of those processes, we also can estimate qualitatively about the compression work, rather amount of compression work that would be needed to be supplied. So, if I write here so this is PV plane, and if we assume that the compression process between two pressure P equal to P 1 and this is P equal to P 2. So, these are the pressure limits, and if we now consider the process is, so this is point 1, this is point 2 and then this is 3. So, 2 to 3, that is, so basically that from pressure P 2 to P 3, that is what is needed of the process. We need to raise the pressure of the working fluid, and if this is the say this is PV power gamma equal to constant. So, this is the process. Now, if we consider the compression process is reversible isothermal. So, this is 4. So, this is we can write that 2 to 4, that is reversible isothermal compression, and then what would be reversible polytropic process. Then what would be the reversible polytropic process? Reversible polytropic process is in between these two, and so this is 3 prime. So, 2 to 3 prime, so this is reversible polytropic compression. Now, question is, from this PV plane we can easily see that work done, that is certainly area under this process curve. So, the work done, if we now fix the pressure limit between, so if we write here for the pressure limits that is P1 and P2, if the pressure limits are P1 and P2, then for gamma less than n less than 1, work done or work input to the compressor following reversible adiabatic process is greater than work input following reversible polytropic process, which is greater than following reversible isothermal process. So, this is basically what we can see without going into the mathematical calculation, but without going for the mathematical calculation, just from the graphical representation of the process lines in PV plane, we can assess certainly qualitatively about the work that we need to supply to the compressor for the compression process. Okay. Now, if we recall in the last class that also from here we can see that work to be supplied to the compressor following a reversible isothermal process is certainly less as compared to the work needed for other two processes, work that should be supplied to the compressor following other two processes. That means, if the process is reversible adiabatic process, compression process of course, then amount of work to be supplied to the compressors is maximum. So, if the work input to the compressor is significantly small than the work required for the compression following reversible adiabatic process, then it would be more economical performance wise to have a reversible isothermal compression, because we had seen that a significant part of the turbine work output is consumed by the compressor for the compression process. Now, For the reversible isothermal compression, as I discussed in the last class, it is very difficult to achieve and it is not of that much use in practice. And in a reversible isothermal compression, work done on the gas during the process is transformed into an increase in the internal energy. So, if we write the isothermal compression, then we can write del W plus du equal to del Q, right. Now, in the for the reversible compression process following isothermal compression, the amount of work that is done on the gas, certainly if the working fluid is air or any ideal gas, that work solely, I mean certainly we are supplying certain amount of energy in the form of work, and that work done on the gas during the process will be transformed into an increase in the internal energy. That means, this del cube equal to del W plus U2 minus U1. So, 1 to 2, 1 to 2. Now, we know that for an ideal gas, internal energy and enthalpy is function of temperature only. In fact, internal energy and enthalpy of an ideal gas is not function of volume and pressure as well. So, it is dependent on temperature only. The process is isothermal compression. So, we are not allowing the temperature to be increased during the compression process of the working fluid. So, U equal to function of temperature only for an ideal gas, and we can see that the temperature is remaining constant during the compression process. Hence, we can write this del Q equal to del W. What does it mean? Because this fellow equal to 0 for reversible isothermal compression, right. So, what we can understand that the amount of energy that is supplied to the compressor in the form of work for which rise in temperature will be there, but isothermal compression is not permitted to have an increase in the temperature of the working fluid. The sole purpose is to increase the pressure. So, what would be the case, because we can see that del Q amount will be there because if you are supplying certain amount of work and that will give rise to certain amount of heating. So, that energy will be taken from the gas by the cooling. So, basically for isothermal compression, the amount of energy you are supplying in the form of work and the rise in temperature is not permitted. Hence, this amount of energy will be taken from the working fluid by cooling. So, this is very important that isothermal compression sole purpose is to develop pressure only or raise pressure only. Okay. So, now let us discuss about the compression efficiencies. In one of the previous classes, we have talked about isentropic efficiency of the compressor. As such, we had seen that degree of irreversibility, that irreversibility is present with the compression process, and it is because of that reason isentropic efficiency, that is the actual work that should be supplied to the compressor for the compression of the working fluid would be more. Now, today we shall discuss about compression efficiency. One is compressor efficiencies. So, the first one is adiabatic efficiency. So, eta compression adiabatic efficiency. What is this? This is very important, that actual amount of work to be supplied, actual work to be supplied to the compressor. And this is work input to the compressor following reversible adiabatic process. So, if we try to recall the TS plane, so these are the pressure limits, and this is 1, this is 2, but in reality the actual process should be this is 2 and this is 2s. So, if we write here, this is actually H2S minus H1 divided by W actual. That means, if we apply steady flow energy equation across the compressor, then the work needed to be supplied for the compression process is H2S minus H1 following isentropic process. So, this is eta compression adiabatic. Similarly, we can write eta compression isothermal. What would be this? Isothermal, basically that it is again actual work to be supplied and work input to the compressor following reversible isothermal process, right. Now, if you recall, today only we have discussed that work input following reversible isothermal process is lesser than the work input following reversible adiabatic process. So, if we assume that this is W isothermal divided by W actual, what we can say that eta, since this is very less, right. So, eta compression adiabatic is greater than eta compression isothermal. Right. Now, it is sometimes it is even greater than 1. Eta compression adiabatic is greater than 1. So, that is what we can see. We shall discuss about another efficiency, that is called volumetric efficiency. of the compressor. So, you know that if we try to draw again the PV process in the PV plane, we are assuming say this is P equal to P2 and this is P equal to P1. So, this is two pressure, these are two pressure limits, and if we consider that one to 2, that is the suction, or I should give name, say this is A to B. So, this is A, this is B. A to B is suction, and so this is the clearance volume Vc and this is the swept volume Vs. So, this is the swept volume Vs. So, Vc is the clearance volume and Vs is the swept volume. So, this is basically, if you consider this is a reciprocating compression. Now, A to B is the suction stroke and then B to C is the compression process following a reversible adiabatic compression. Then C to D is the process which is discharging high pressure working fluid to the combustion chamber. So, let me tell you once again, and then finally again another process will start, that is cycle will start and it will start from A to B. So, A to B is the suction, then B to C is the compression and C to D, that is the process at which high pressure working fluid is discharged into the combustion chamber. Now, question is, from this particular diagram we can define what would be the volumetric efficiency. So, volumetric efficiency is basically defined eta volume. Ideally, you try to understand that this is the swept volume. So, pressure is getting reduced from D to A inside the compressor. So, basically expansion. So, piston is again coming down and then suction stroke starts. So, this is the swept volume. So, this is the piston displacement or swept volume. That means this is the stroke, and if the piston is now getting displaced from upper between these two locations, I should say. So, ideally it is because of this piston movement we are supposed to get a volume of air inside the cylinder which is equal to Vs, and that is the swept volume. So, again I am telling you, process A to B is the suction stroke, B to C is the compression stroke. When compression stroke ends, then pressure that high pressure working fluid will be discharged into the combustion chamber, and then when pressure is still at P2, then finally again there is an expansion because piston has to come to the another pressure. So, that is pressure inside the cylinder should be again suction pressure at P1. So, essentially we are trying to have, this is the swept volume. Ideally we are supposed to have volume of air that is equal to Vs inside the cylinder, but actual volume of air or any working fluid drawn into the cylinder during suction stroke. So, this is the volumetric efficiency. That means, ideally you are supposed to have, this is Vs, this amount of this volume of air inside the cylinder, but we are getting another amount of working fluid or air into the cylinder, and the ratio of these two is known as volumetric efficiency. Certainly, actual volume of air that should be drawn into the cylinder during suction stroke is not equal to the piston displacement or swept volume. So, if we write it, so this is m dot into V1 divided by Vs, where m dot is mass flow rate of air or any other working fluid, and V1 is the specific volume of air or any other working fluid at compressor inlet. So, this is the definition of this volumetric efficiency. So, now question is, I have drawn this PV diagram here only to establish another important relation between the geometrical configuration, that is swept volume, clearance volume of the compressor, and the volumetric efficiency. So, this eta volume metric efficiency equal to m dot V1 divided by Vs, right, that we can see. And so, what is this? Basically, that if we try to go back to the previous slide, this is the actual volume of air that should be drawn into the cylinder, that is Vb minus Va. So, this is Vb, this is Va. So, Vb minus Va, that is the actual volume of air that should be drawn into the. So, this is Vb minus Va divided by Vs, right. So, Vb minus Va divided by Vs. Then what is Vb? Vb is, that is Vs plus Vc. So, we can write that equal to Vc plus Vs minus Va divided by Vs. So, we can write here that equal to 1 plus Vc by Vs minus Va by Vs. So, this Vc by Vs is this Vc by Vs, that is known as clearance. So, this Vc by Vs, basically the ratio of clearance volume to the swept volume is defined by another term that is called clearance CL, and that is called clearance. So, if we write here that equal to 1 plus CL minus Va by Vs. So, we have to relate this Va by Vs in terms of the pressure ratio, and then we can close the expression of this volumetric efficiency. So, if we go back to this, you know that the pressure ratio is P2 by P1, right. So, what we can write from this expression is that Vd by Va equal to P2 by P1 to the power gamma minus 1 upon gamma, right. So, else what we can write, if we assume that this process is P50 to the power gamma equal to constant, or more generic process, if we assume that P50 to the power n equal to constant, then what we can write? We can write for the process D2A, we can write P2, we can write P2 Vd to the power n equal to Pa, this is Pd, and Pd equal to P2 and Pa equal to P1 Va to the power n. Therefore, we can write one step further, that is P2 Vd to the power n equal to P1 Va to the power n. Therefore, we can write Va by Vd, that is P2 by P1 power 1 upon n, right. This is what we can write. Now, what is Va by Vd? So, you can see Va equal to Vd equal to Vs, Vd equal to Vc, that is the clearance volume. So, that means we can write one step further, that Va by Vd equal to P2 by P1 power 1 upon n. Va equal to Va divided by Vc equal to, because if we go back to the previous slide, we can see Vd equal to Vc. So, what we can do, Va equal to, so we can write here that Va by Vs equal to Vd by Vs P2 by P1 power 1 upon n. And you know that we need to know about this Va by Vs to close this expression, and here Vd by Vs equal to Vc by Vs into P2 by P1 power 1 upon n, because Vd equal to Vc, that is the clearance volume. I should say this is clearance volume. So, this is VCL. So, this is VCL, and if we go here, then I should write here, that is VCL. So, VCL and VCL by Vs, that is Cl. So, next, otherwise it will be confusing, because I have also used the point C here. So, next what we can do, Vd equal to VCL. So, that is, this is Cl into P2 by P1 power 1 upon n. So, what we can do, we can next write that volumetric efficiency eta volume equal to 1 plus Cl minus Cl into P2 by P1 power 1 upon n. So, you understand that volumetric efficiency will be reduced if we need more RP, pressure ratio. So, that means if we need to raise high pressure of the working fluid, then volumetric efficiency will reduce. What are the possible reason behind it? Possible reason behind it are, or I should say the possible reason behind it is the leakage, because if we need to raise high pressure of the working fluid through the compression process, certainly leakage of the working fluid will be there, and hence it will eventually reduce the volumetric efficiency. Okay. So, with this, now let us discuss about the important part of this unit is called multistage compression and intercooling. So, basically if we need to go for multistaging of the compression process, intercooling is needed. So, let me tell you one thing, why we need to go for multistaging. First of all, if we try to recall, in the compression process, the sole purpose is to raise the pressure with an appreciable increase in density, as well as increase in temperature as well. So, basically that if we need to increase the pressure as well as temperature, when we need to supply compressed air promptly to any combustion chamber, for that we need to go for multistaging compression. I shall be discussing today why we need to go for multistaging, and if we need to go for multistaging, intercooling is very much essential. So, these two this coupled keywords multistage compression and this is coupled keyword and intercooling, these two are basically directly related. If we need to go for multistaging compression, we need to go for intercooling. Now, as we have discussed that if the compression process is needed only to increase the pressure of the working fluid with no increase in temperature, then multistaging may not be required, but it is very unlikely that we will be having a compression process wherein sole purpose will be to increase substantial amount of pressure without increasing temperature, otherwise isothermal compression will not be possible. So, if we need to increase the pressure, so if we go back to the previous slide, we can see that if we need to increase pressure from P1 to P2, then we can understand that pressure ratio Rp that we could define in the last class. So, for such a increase in high pressure, if the requirement is not only to increase pressure, but also to increase temperature, temperature of the working fluid at the end of the compression will be so high that that temperature will be having some detrimental effects for the mechanical component of the compressor. Now, that is one thing. Second thing, that means multistaging is needed if we need to increase the pressure of the working fluid substantially, then instead of a single stage compression, we need to go for multistage compression. Why? Because multistaging compression would provide a few distinctive advantageous feature. So, basically if I write, it will reduce the work of compression. Whatever I am writing here, those points I am writing here in basically these are advantageous features, and these features will be very important to ensure when there will be a compression process, and the sole purpose of the compression process will be to increase a substantial increase in pressure. Now, we also can increase that pressure using a single compression or single stage compression, but if we perform a single stage compression to develop such a high pressure, then whatever points I am writing here, all these advantageous features will not be there. So, that means the work of compression will be more. So, the compression work would be more, but if we use multistage compression, then that multistaging reduce the work of compression. Number 2. So, all these are, if I write here, multistage compression. Then let me write here quickly, then coefficient of performance increases. 3, you know, few minutes back I said here that sometimes adiabatic compression efficiency becomes higher, greater than 1. Efficiency cannot be greater than 1, then we need to define coefficient of performance. So, the coefficient of performance will be more if we use multistage compression, but again I am telling you, you have to be, you know, very careful that all these points we are trying to compare, all these points we are writing here, we are discussing here, only when we are comparing the compression process, that is multistage compression vis-a-vis single stage compression. If we need to increase a substantial pressure of the working fluid, then if we go for single stage compression, all these favorable aspects or advantageous features will not be there. COP increase, and then leakage past the piston or leakages past the piston are reduced, or and number 4, volumetric efficiency increases, of course eta volumetric compression. So, this is what we can see. So, this volumetric efficiency will increase, now next point is point 5, that is size of the cylinder can be optimized. So, size of the cylinder can be optimized. So, see, few minutes back we have discussed that volumetric efficiency is function of pressure ratio. If this pressure ratio Rp equal to P2 by P1 is very high, then volumetric efficiency will reduce, but if we use instead, you know, the multistage compression, then volumetric efficiency will increase, otherwise it will reduce. Again I am telling we need higher compression ratio, that is P to be more. Okay. So, now question is, for this multistage compression, again as we have discussed that the sole objective is to increase high pressure of the working fluid with an appreciable increase in temperature. Even we need to go for multistage compression, an important aspect of the multistage compression is to use an intercooler. Why? because if as I said you that at the end of the compression process not only the pressure will certainly increase, but along with the pressure temperature of the working fluid also will increase, and if the temperature increases beyond a threshold value, that high pressure and high temperature working fluid, in particularly high temperature working fluid, will be having detrimental effect on the mechanical component of the compressor. Second thing, it is easier to compress heavier cold air or any other gas rather than hot air. So, accounting for this, intercooler is placed between two compressors if we need to go for multistage compression. So, I am writing here intercooler. Intercooler, its main function are number 1 to reduce temperature of the working fluid before it enters the next stage of compressor. Right. Actually, if we need multistage compression, the working fluid that comes out from the first stage or first compressor will be having high pressure and high temperature. Ideally, inlet condition of the inlet temperature to be precise, not only pressure, but inlet temperature of the working fluid of this at the or temperature of the working fluid at the inlet of the second compressor ideally should be equal to very low and as close as the ambient temperature, but for that this intercooler is used. So, I am writing here that for the compression in the second stage, ideally air or working fluid temperature should be as close as to the ambient temperature. As possible. It is very difficult to bring the temperature of the working fluid close to the equal to the ambient temperature, but our objective should be to bring or to reduce the temperature of the working fluid before it enters into the second stage of compression closer to the ambient temperature. So, this is why intercooling or intercoolers are placed. And second thing that as I said you that it is very easier to compress hot, it is easier to compress cold heavier air than hot air, and if temperature increases, temperature will certainly increase, and if temperature increases beyond a threshold value, then that high temperature will be very much difficult to handle by several mechanical components, those are there inside the compressor. Okay. So, with this now let us just schematically discuss that about this intercooling effect. So, I am writing here intercooling effect. So, if we consider, so this is air is coming, then air is taken to another mechanical component, then that air is taken to another compressor. So, and that air, so basically you know that is air intake. So, this is low pressure cylinder, this is high pressure cylinder, and so the air is first taken into this low pressure cylinder, it is now compressed, and that air which is coming out from the low pressure cylinder is now taken in this intercooler. So, this is intercooler, and inside the intercooler that air releases heat, but we need to maintain that pressure will be equal to either the low pressure cylinder or a pressure which is in between these two cylinder pressures. So, we will be discussing today on that aspect, and then that air is again taken to high pressure cylinder and again further compressed. So, this is basically cold air, and finally, that discharged air is discharged, and this discharged air at delivery pressure. Okay. So, now question is, we need to reduce the temperature of the air before it enters into the second stage of turbine. As I said you few minutes back, what is done here, that here cold water is allowed to pass through this intercooler, and taking water, this is hot water. So, basically that air releases heat to this water stream, water temperature increases. By releasing heat, we can reduce the temperature of air before it enters into the cylinder, second cylinder or second compressor. As I said you, ideally it should be very much favorable for the compression process. Of course, if we can reduce the temperature of the air as close as to the ambient temperature, but it is not really possible, but we need to reduce the temperature, and finally, the air will be again compressed and it will be discharged at the delivery point. Now, as I said you that this cooling should takes place at a pressure which at least should be the pressure at which the which should be at least at a pressure, and that pressure is developed by the first cylinder, or it should be in between a pressure which is in between the pressure developed by the first cylinder and pressure that would be developed by the second cylinder. So, that would be an intermediate pressure stage. So, this is basically the intercooling effect. Now, if we try to map the processes in PV plane, so if we try to map the processes in PV plane, then we can see that, so this is P equal to P1, this is pressure, this is volume, and say this is P equal to P2. So, we need to increase pressure of the working fluid from P1 to P2, there is one case that if we use a single stage compression, then we certainly can develop the pressure from here. So, this is 2, say this is 0.1 and this is 3, and 2 to 3, say this is PV to the power n equal to constant. Okay. Now, if we increase the pressure using a single stage, those problematic issues will be there: reduction in volumetric efficiency, reduction in COP, work input will be more, and the rise in temperature at the end of the compression process should be so high that the rise of the that high temperature of the working fluid should have or will have detrimental effect on the mechanical components of the compressor. What is done here? Now, say for example, now if we, it is compressed in the first cylinder up to an intermediate pressure, say this is the intermediate pressure, 3 prime, and then it is, so process 2 to 3 prime, that is basically compression in low pressure cylinder, and this is compression in a single stage cylinder or compressor, single stage compressor. Then what is done? 3 prime to 4, so this is 4, that is delivery of compressed air in low pressure. So, this is delivery of compressed air or any other working fluid at low pressure, right, or in the low pressure. So, it is this is in low pressure. Then finally, again we should be having another process, that is 4 to 5, and say this is the point and this is 0.5. So, 4 to 5, that is basically rejection of heat at intercooler, and then 5 to 6, that would be compression at high pressure cylinder. This is compression in the high pressure cylinder, right. So, now these are the processes, and finally 6 to 7, that is delivery of compressed air So, what we can understand from this particular diagram is that this is the amount of work which we do not require because of this multi-stage compression. So, we are allowing compression process from 2 to 3 prime in low pressure stage compressor, then 3 to 4, that is basically 3 prime to 4, that is delivery of compressed air or working fluid in low pressure, then 4 to 5 is essentially again release of heat from the compressed air to the another fluid, inside the intercooler, and finally 5 to 6, that is again rise in pressure of the working fluid in a high pressure stage compressor. So, had we performed the compression process by using a single stage compressor, certainly the pressure at the end of the compression would have been P3 or P2. So, our objective is to rise the pressure from P1 to P2. So, there are two possibilities. One is that we can use a single stage compressor and the pressure will increase from P1 to P2 following this process 2 to 3. In another case, what we are doing, we are using multi-stage compression, we are developing pressure from 2 to 3 prime first, then by having certain another mechanical arrangements, we are developing pressure from again intermediate pressure to the final pressure, but in that case what we are doing, we are saving this much amount of work. So, this is saved work due to multi-stage arrangement, right. Had not we performed the compression process by using multi-stage compression, we would have certainly got pressure at the end of the compression, that is P2, but in that case this much amount of additional work would have been needed to be supplied to the compression. So, this much amount of additional work would have been needed had we performed the compression process by using a single stage compressor, but what we can do now, we can save this much amount of work because of this multi-staging arrangement. But mind it, for this multi-staging arrangement we can save this much amount of work, that is true, that will certainly increase the cycle efficiency, but what is most important, that we need to have an important mechanical component or mechanical arrangement, that is intercooler. So, what we need to do? We need to supply again one coolant that will take away a certain amount of energy from the flowing gas or air or any other working fluid. To have such an arrangement, the system will be bulky, and for that both operational cost as well as maintenance cost would be there. Second thing, it is because of this reduction in temperature of this working fluid inside the intercooler, though we are getting certain amount of benefit in terms of work needed to be supplied to the compressor, and that is this much amount, but what will happen, the amount of energy that should be added to the system, because the cycle efficiency is net work output by net energy input. So, what will happen, instead of having an increase in the cycle efficiency, eventual impact would be a reduction in cycle efficiency. So, multi-stage compression with intercooling is needed because we need to run the unit for a long time, and for that we need to ensure that even if we need to compromise with the cycle efficiency, but at least we can run the unit without inviting additional problems like failure of mechanical component because of the rise in temperature and many things others. So, to summarize today's discussion, we have discussed about the compression processes and work needed to be supplied to the compressor for the compression process following reversible adiabatic, reversible isothermal and reversible polytropic processes. Then we have discussed about several efficiencies of the compression process. Finally, we have discussed about the requirement of multistage compression, and for the multistage compression we had seen that intercooling is very much essential, and if we need to go for multistage compression, certainly intercooling will be there, but this arrangement eventually reduces the cycle efficiency. We stop here today and we shall continue our discussion in the next class. Thank you.